Hi there, welcome to Ben's Astrophotography. This is the third video of my detailed narrowband processing series. If you haven't watched the overview and phase 1 video, please use the shortcut on your upper right to check them out. They are highly recommended. In phase 1, I cleared the gradient from light pollution, registered and normalized all three masters, then cropped them identically to have a clear cut. These are all preparations. Now in this phase, I will do some real processing. I call this phase 2 as linear processing. Let me start with a H-alpha master frame here. You see, this is almost pitch black. This is because it is still in its linear stage or not stretched. It means every single pixel on this frame, the signal strength readout is 100% proportional to the amount of photons this pixel has received during the whole exposure. In other words, this is a raw image. As you have probably learned from other photo processing, there are a lot of algorithms that will be more effective on raw images. In astrophotography, that includes deconvolution and MLT noise reduction. So I will cover these two steps in this video. In order to see what's there, let's do a on-screen stretch, automatic stretch here. And I will zoom in a little bit to 200%. On this magnification, you can see that the stars are they are round, but they are not pinpoints. Theoretically, if we have a perfect atmosphere and perfect lens, also the optical system, each star should appear as just one pixel on our CMOS. But apparently this is not the case here. This is because number one, our atmosphere is not perfect. It has all these turbulences in between. Also, our opticals are not perfect either. So there's some convolution caused by the whole system. That's why pinpoint one pixel star appeared as an airy disk on my CMOS on the final image. The idea of deconvolution is that now I know a pinpoint star appears as an airy disk on this master light frame. So I can reverse engineer to deduct back to what it should appear. To do that, I should collect some star profiles and average them out to get a standard star profile and use that to roll back this convolution process that's called deconvolution, remove this convolution, arrive at a sharper image. So I would say this is a pure mathematic algorithm to improve our image quality. That's really nice, right? So let's start by making the star profiles. This is the process that we should use. It's called dynamic PSF. I should probably choose several dozens of stars to reach at a good averaged star profile. To do that, I will pick 8 stars on each spot of this image, and I'll go to each corners, like 9 parts of this image, and on each part I will take 8 stars. Let's start. To choose a star, you only need to move your cursor close to a star and left click on it. Let's do that. 3, 4, 5, 6, 7, 8. So here I have a Lorentian. I should delete that because it's sharp enough. I don't need that. And also I have a Gaussian, which means it's already saturated. I don't want to use that either. So I will choose 2 more stars. Okay, this is the center of the image. I will go up and choose 8 more stars. 1, 2, 3, 4, 5, 6, 7, 8. Okay, here I have one Lorentian and I delete it and pick one more. That's good. Do the corner. 1, 2, 3, 4, 5, 6, 7, 8. As you can probably find out, the stars on the upper right corner is not ideal. I do have some commas here. A lot of my friends complained that this process of selecting stars is quite tedious. But the way I look at this is that every single move between these stars, I'm kind of doing a space travel of hundreds or thousands of light years, which is pretty cool, right? But at least for me, this makes this job more enjoyable. Hope that will work for you too. So here I have all these groups of star dots that I have chosen. I'll come back here. Because these stars are pretty much randomly chosen, I need to do some filters to get me the good data. First, I need Moffat stars. It's either Moffat or Moffat 25 or Moffat 6 here. So they are all good. But I need to delete all these Gaussian and the Lorentian stars. So here it seems that I don't have any Gaussian or Lorentian, which is great. Okay, this is filter number 1. Number 2, I need to use this one to sort the beta exponent. I should delete anything less than 1.5 in the beta. So here I have 1.0 and 1.5. I should delete them. And also, if I go all the way down, I need to delete all these outliers. So here 10 is definitely an outlier. I would say the majority of them should fall in 7. Let's say 7.2, right? These, I think they are outliers. I will delete them. My advice is that don't hesitate to delete the bad data, because the quantity here doesn't really matter, but the quality does. So let's delete these. This is the second filter on beta component. Then I'll go to mean absolute difference, MAD, and I should delete those that are exceptionally big. I would say this line draws on 2.5, okay? I will delete all these 2.5, bigger than 2.5. The last one, the fourth filter, is the aspect ratio. I will delete the very small aspect ratios. That's, I believe, just one here. I'll delete this one. So now I have around 49 stars. I will choose them all, Control A, and do the picture. Okay, now it generates a small PSF, the star profile. I have no use of this one, so I close this window and zoom in a little bit. This is a very small star dot. That's because I haven't stretched it. If I stretch it, it looks like this, okay? So I'll put this aside. And then now I'm ready with this star profile. I'm ready to do the deconvolution. But before doing that, I need to have some previews. Let me change this to H alpha. I can click on this create new preview and choose some interesting areas on this picture as a sample. Because when doing deconvolution, I need to do some trial and fail rounds. I don't want to execute the whole algorithm on the whole image. So that's why I need some small windows of previews. Like here, I have a dark background preview. And here I can have a preview on the shades of the nebulosities, like this. Okay, let's go to the preview, my first preview, and I should use the deconvolution. Make sure you choose the external PSF, get this right star profile. The most important part here is de-ringing. I will show you, I will put both of them at 0. I'll try this, okay? You see there are some black circles, black rings among each stars. That's definitely no good. So I should increase this global dark to fix it. Let's start 0.5. Okay, this still looks bad. So let me increase this more. Okay, this looks better, but it could be more. So I will increase it to 0.02. All right, but still on the left side, there's some dark rings again. So I will increase this one more time. Okay, now I should use Ctrl-Shift-Z to toggle around back and forth between these two. So you see the star gets shrink, but I still see some black rings around the star. So let me increase this. Why not? Go up all the way up to 0.32. I think now it looks good. One thing I should mention here is that if I toggle back and forth, you can see it's not only the stars get smaller, the nebulosity gets sharper too, right? That's simply because, like I said, it's more a deconvolution to improve the image quality. Stars is just a tool to do the rollback or reverse engineering. But this algorithm should be really applied to the whole image to improve it globally. So this looks good. I'll move on to the next preview. This is dark background. Okay, let me enlarge this one. Okay, back and forth. In the background, I see a little bit of shrinking of the noise, which means the noise gets more accentuated in the background. Let me just increase this global bright a little bit, like 0.01, to see, yeah, I think it's good now. Okay, let's go to preview number 3 and toggle back and forth, back and forth. You see this nebulosity gets sharpened a little bit. So I will apply this deconvolution to the whole image, like this. It will take a little bit of time. Let me fast forward for you. Let's enlarge a little bit and see how it works, just to confirm. Let's do Ctrl-Z and Ctrl-Y. The nebulosity gets sharpened. Also, the star shapes are shrinked a little bit. Okay, that's good. Next, let me move this image to the other workspace, which I have the MLT noise reductions. Now let me zoom in and show you some noises. Okay, it's not very significant, but still there are some noises which I want to get rid of before going to non-linear phases. One of the biggest advantage of using PixInsight is that we can use masks to protect the area that we don't want some effects to be used. For example, if I'm doing noise reduction, for sure, I want the dark areas to be reduced more for the noise. But for the bright areas, actually, I want to do some sharpening on it rather than noise reduction. So I should protect them from noise reduction. Also, the star dots. I don't want to have any noise reduction on the star dots. To do that, let's make a mask. I will simply duplicate this black and white picture and use it as a mask. But one tricky thing here is that, remember, this has been stretched automatically on the screen only. It's not a real stretch. I will remove this on-screen stretch. With this almost black image, I cannot use it to protect the areas for noise reduction. So I need to do a real stretch. I will use these two processes. First, screen transfer, I will do automatic screen transfer again. And I will move this triangle into the histogram transformation, and at the bottom line here, I will release it. And the change will be automatically shown here. So I will apply this histogram. This is a real stretch. I will apply this histogram transformation onto this mask image. It becomes super white here. The reason is that I have both the real stretch and the on-screen stretch on it. So let me remove this on-screen stretch. This is a real stretched image. This looks good. So I will drag this image and drag it to the image that I want to use this mask for. When this shows as a square, I release the mouse. Now it's automatically become the mask on the other image. The red part of this image means that these parts are actually protected, which is not correct, right? Because I want the stars and the bright areas of this image to be protected, right? So I will choose mask and invert mask, or Ctrl+Shift+I to do it. Okay, now it looks like it, right? So also, if I don't like this mask, I can disable the show mask. Now it's good. Let's go to preview 1 again. I don't need these two. Okay, now I have this MLT noise reduction. Here we have quite a few settings, so that's why I use this icon to just save this settings. I don't need to input it every time. I will just apply this right away. Oh, by the way, these numbers, I got them from the Light Vortex Astronomy website. That's a very good website. It's highly recommended. So here, let me drag and drop this triangle onto the preview. Let's zoom in and toggle back and forth. You see, the noise reduction is quite obvious. And let's go to the background preview again and see how it is. Okay, this makes the background really smooth. That's great. And this one, before and after, before and after. Okay, I think it's good. It really reduces quite big part of the noise. I will apply this one to the whole picture. And that's it. Of course, I should duplicate these two steps to O3 and S2 masters as well. I know this needs some real patience and practice here, but I can assure you, this is worthwhile to develop a sharp image with high SNR. Let's wrap up. For this number 2 linear phase, there are only 2 steps: deconvolution and MLT noise reduction. Let me use Ctrl+Z to go back 2 steps. Now I'm bringing in deconvolution. The stars get shrinked and the nebulosities sharpened. Then this is MLT noise reduction. I'm bringing it back. It's subtle, but on the dark parts of the image, noise really gets reduced. Now we are done with phase 2. By the way, if you don't want to miss out my next videos and you haven't subscribed yet, please do that now. Thanks for watching. I'll see you next time. Clear skies.